This is the Introduction to Computing and Programming in Python, a multimedia approach, making sounds by combining pieces, and this is Chapter 9. So the chapter objectives for Chapter 9 are to blend sounds so that one fades into the other, to create echoes, to change the frequency of a sound, to create sounds that don't exist in nature by composing more basic sounds, sine waves, to choose between sound formats such as MIDI, MP3 for different purposes. The computer science goals are to use path files to reference files at different places on the disk, to explain blending as an algorithm that crosses media boundaries, and to build programs for multiple functions. So making more complex sounds. We know that natural sounds are often the combination of multiple sounds. Adding waves in physics or math is hard. In computer science, however, it's easy. Simply add the samples at the same index in the two waves. So we can see in this example, we say for source sample in range of 0 to the length of the source, the destination value variable equals the sample value at the destination, um, comma, the source sample. Source value equals get sample value at source sample. And then we set the value, source value plus destination value. So we see that we're adding sounds. The first two are sine waves generated with Excel. The third is just the sum of the first two columns. So A, B, and A plus B equals C. Uses for adding sound. We can mix sounds. We can even know how to change the volume of two sounds even over time, fading in or fading out. We can create echoes. We can add sine or other waves together to create kinds of instrument sounds that do not physically exist, but which sound interesting and complex. Blending two sounds. So here's a function that you can take as an example. Um, we won't actually even go over it because we don't actually have the wave files that that this has. Um, but if you look through it, it's things that we have used before, that we're familiar with. So we see a lot of for loops in there. We see some get sample values at. We see a play, we see a return. So everything in here is things that we understand, right? It's just how they want to mix the two sounds. A function for adding two sounds together. So we see we define a function called add sound into, and we see sound one, and we see sound two. And then we can see that we go through each uh, each sound file that we have, sound one and sound two, and we actually just add them together. Notice that this adds sound 1 and sound 2 by adding sound 1 into sound 2, making a chord by mixing three notes. So here we have C4, E4, and G4, which we have that go to the bassoon wave file. All right, so we get media path, make the sound. We do all that at one line. The add sound into combines E4 and C4, and then we play C4, and then add sound into G4 and C4, and then we play C4. So at the end, C4 should be E4, G4, and C4 all combined. Adding sounds with a delay. So we see make chord, which is the function. We mentioned it, but we didn't actually don't have actually had a function. So here we have we define make chord as sound one, sound two, and sound three, and we go through the range from zero to sound the length of sound one. We get the sample value for sound one. If the index is greater than 1,000, then we use sound two, and then if it's greater than 2,000, we use sound three. Note that this is the version we're adding into sound one. So this all makes sense. Again, you can try this out with sound files that you have yourself. If you want to use the antelope, three different antelope sounds together and test this out, go for it. But what it's actually just doing, in all in the end, all it's doing is for the first 1,000 samples, um, it's playing sound one, the next 1,000 sound two, and the next 1,000 sound three. Creating an echo. So we define a function called echo, and then we have the sound file, SND file. Not really the best variable name, but we can kind of understand what it means. And then we say comma delay. So we make sound. We make two sound files, right? what an echo really is just the repeating of the sound, right? So sound one, sound two, we make two copies of it, and then we actually delay the combining of it by a specified delay that we have, right? So we still go through the sound file, and then we multiply the sound file by zero point 0.6, right? And then we say index minus delay. So, and then we combine them together. So what it's actually doing, it creates a delayed echo sound, multiplies it by zero point 0.6 to make it fainter, and then adds it back to the original sound. Cool. What is the SND file in echo's function? Right, we mentioned that. Is it the path to a sound file, a sound we're going to make echoes from, or a base file name like wave that we're going to use to get media path? So let's look how sound is used. So we can see that we pass the sound file parameter into the method make sound, which means that we already know that it's not a sound file. Oops. We know that it's not a sound file. So number two is wrong. Is it the base file name that we're going to use with get media path, or is it the path to a sound file? So let's go back and look at what make sound takes. Oops. So if we look at our JES functions, we go to sound, we see make sound. It takes the path to the wave file, right? So we for sure know that one, the path to the sound file is the correct. So how the echo works. Top row is the sample of our sounds. We're adding it to us, but delayed a few samples down and multiplied to make it softer. So we can see 100, 200, 1000, and then we can see that we add in the echo. So here's our original sound, right? Here's our sound 2, multiplied by zero point 0.6, right? So it's 60, 120, 600. So we can see this multiplied by zero point 0.6 is this row. And then we add these two together with a delay, which this is the delay amount, and we start right here, right? And we can see that that's the combination. Could you go past the end of the sound? If you're adding two sounds together, one offset by the delay, couldn't you go past the end? Is it absolutely you only want it to do this with the short sounds? No, we're going to end at the end of the sound with the for loop. Yes, so we make the target sound extra big to make space. So in this example right here, right, we do get length of S1. So we actually answered it by using number 2, um, because the for loop only goes that far, right? So we're not going past the for loop, so number 2 is the correct answer. Echo with a single sound. Here we define a function called echo. It takes delay and sound again. It uses the same sound function, but it does index minus delay in value 2 here to actually get the echo sound. But similar to what we just went back. There's an echo with feedback. You can take this example if you want to. I'll pause it here for a second just so you can copy it down and test it. How sampling keyboards work. They have a huge memory with recordings of lots of different instruments played at different notes. When you press a key on the keyboard, the recording closest to the note you just pressed is selected, and then the recording is shifted to exactly the note you requested. The shifting is a generalization of the half/double functions that we saw earlier. Doubling the frequency. Here's an example of this. And then noted here, y the +1. We want to do half, in case it's like an odd number, we can do +1 just to make sure that it's always going to be the right. Or sorry, so it's 1 past the midpoint. And then this 2 here means that it's actually going to, I don't know if we can actually, oops, sorry, let me do it here. I'm not sure if we can see what it's expected. Range takes 1 to 3 arguments, but I don't know if I can see what range takes. So if you actually look it up, you'll see that range does take it could take 2 arguments, so it could be 0 through the max number, or it could take 3 arguments. It could be the min, max, and then it could be like the space in between, right? So this is 2, so it's going to take every 2, right? So that's how we double the frequency in this example. Again, everything that we've already went through. I'm not going to repeat this because it's pretty straightforward because we've already learned all these functions here. Having the having the frequency, dividing in half. Here's the piece that does the halving here. Can we generalize shifting a sound into other frequencies? This way does not work. So we can see shifting, make an empty sound with the length, and then we're setting the index from 0 to the length of the target. We we get the sample value at each target index as we go through, and then we play it, return it, and play it at the end. Watching an hour. It will work for shifting down, but not shifting up. Why? So hello, pick a function. We print hello, and we see that it's the wave file. Lower hello equals shift, and then hello, comma 0.75, which is the factor, and then 1.5 is the other factor, and then we actually get I wasn't able to do what you wanted because the index is out of bounds. So let's go back and look at that, and we can see here, right here, that the factor must be for it to go through the for loop properly. If this is actually higher than more than 1, it's going to go outside of that for loop range, right? So this is why it does not work. So right, so 0.75 worked fine, but 1.5 didn't work because it went outside the max number in our range, and you get the array index out of bounds error that we see here. We need to prevent going past the end of the sound. So what they do here now instead is that if the source index is greater than the actual length, so if we're gonna go out of bounds, just set the source index back to 0, just to prevent that issue. Now we have the basics for a sampling synthesizer. For a desired frequency f, we want a sampling interval like sampling interval equals the size of the sound times the function over the sampling minus the rate. How the original sound synthesizers worked. What if we added pure sine waves? We can generate a sound that is just a single tone. See the book. We can then add them together, perhaps manipulating their volume to create sounds that don't exist in nature. Don't have to use just sine waves though. Waves are just waves are square or triangular, seriously, and they can be heard and have interesting dynamics. We can add together we can add together waves of lots of types to create unique sounds that can't be created by physical instruments. We call this additive synthesis. Additive synthesis, as is, isn't used much anymore. Sampling is an algorithm. Think about the similarities between having the sound frequency and scaling a picture larger, or doubling the sound's frequency and scaling a picture smaller. Recall these two functions. So here is when we actually decreased the size of the picture or made the picture bigger that we've done previously. So our programs functions implement algorithms. Algorithms are descriptions of behavior for solving a problem. A problem are or a yeah a problem are a program otherwise are Python functions is an executable interpretation of algorithms. The same algorithm can be implemented in many different languages. The same algorithm can be applied to many different data sets with similar results. Both of these functions implement a sampling algorithm. Both of these do very similar things. They get an index to a source, they get an index to a target, and for all the elements that we want to process, copy an element from the source at the integer value of the source index to the target at the target index, increment the source index by half, and then return the target when completed. This is the description of an algorithm, also called pseudocode. Right, so pseudocode actually describes in normal English what we're actually going to accomplish that can be implemented in the algorithm. Adding sine waves to make something completely new. We saw earlier that complex sounds like the sound of your voice or a trumpet can be seen as being a sum of sine waves. We can create complex sounds by summing sine waves together. These are sounds made by mathematics by invention, not by anything in nature. So to build a sound wave, we want a 440 hertz sound wave. Then we need one of these cycles every 1 over 440th of a second. We need to break this wave into the number of pieces in our sampling rate. Our algorithm. At each entry of the sound sampling index, we want to get the fraction of the sample index divided by the samples per cycle. Multiply that fraction by 2 pi. That's the number of radians we need. Take the sine of sample index divided by samples per cycle times 2 pi. And then multiply the result by the desired amplitude and put it into the sample index. Again, this is not going to be used for you guys. It's just good for you guys to understand, maybe just at a high level, what's actually happening. Just understand more so the methods that are being used and everything. You don't actually need to understand um, the mathematics behind it per se, because you're not going to use it in this, at least in this class, you're not going to use it. So just understand the gist at a high level of what's going on, and that should be fine. So here's our code for the sine wave. I'm not going to actually even go through this because um, it's more complicated than it needs to be for this class. So adding pure sine waves together, we can see we have frequency and amplitude, and then we can compare the sine waves. So left is 440 hertz, the right is the combined sine wave. Here's making more complicated waves, building sounds with square waves. So why do we write sound programs? Aren't there audio tools that can do many of these things? Sure, and that's good enough. If that's good enough. If you just want to use a sound, then simply use tools to generate the noise, instrument, sound you want is fine. Communicating process. What if you want to tell someone else how you got that sound so they can replicate the process or even modify the sound in some way or even make it better? You can write down all the steps in a sound application tool. That's tedious and error prone. Or you could provide a program, an executable process, definition of a process. What is an MP3? An MP3 files are files encoded according to the MPEG-3 standard. They are audio files that are compressed in a special way. They use a model of how we hear to get rid of some of the sound. If there is a soft sound at the same time as a loud, they don't record the soft sound. They use various compression techniques to make the sounds smaller. Wave files are compressed, but not as much, and don't use any smart models to make themselves smaller. What is a MIDI? MIDI is a standard for encoding music, not sound. MIDI literally encodes for this instrument track, turn key number 42 on, then later for this instrument track, turn key number 31 off. The quality of the actual sound depends entirely on the synthesis, the quality of the instrument generation, whether recorded or synthesized. Media files tend to be very, very small. Each MIDI instruction, play key number 42 track 7, is only about 5 bytes long, not thousands of bytes long. Playing MIDI in JES. The function play note allows you to play MIDI piano with JES. Play note takes three inputs. A note number, not a frequency, it's literally a piano key number. C is the first octave is 1, C sharp is 2, C is in the fourth octave is 60, D in the fourth octave is 62. A duration in milliseconds, and then the intensity, literally how hard the key is pressed. So here's a sound example. So we can take this. Let's just try this out. So we're going to define a function called sound, and we're going to go over. Let's go back. So play note 60, 200, 127. Play note 60, 200, 127. I want to copy this a couple times because we know that it's repeat that it. Oops. I can't copy. All right. So paste, paste, paste. So we're gonna have 62, 500, 127. 62, 500, 127. 64, 800. So 64, 800. And then 6600. Yep. And then we have for range 1 and 2. So for I in range 1 to 2. Go over again. And then we say play note 120, 64, 65, 67. So 1, 2, oops, 3, 64, 65, 67. And then we have 120, 120, 60. 120, 120, and then 60. So we're gonna load the program. Would you like to save it? Yes. Let's call it test again. Replace it. Load the program. I'm gonna play it. I'm gonna call it sound. Cool. So I don't know if you guys actually heard that play. It definitely played through my on my computer. So take this example. It's a pretty cool way that you can create your own custom sounds through JES. Um, just if you guys like music, if you guys want to just test some functionality that JES does, what Python does, take this example and try to make your own music if you can. And that's the end of this chapter for chapter 9. I hope you learned a couple things. Again, the sound wave stuff was a little complicated, so just try to understand the gist of it, try to understand the functions and how what they're actually doing, and more so the computer science techniques that are being used, not so much the mathematics behind it. But then go ahead and take the MIDI file and understand that as well. We talked about MP3 and the MIDI itself and how they're different. So just understand that. And as always, if you have any questions, feel free to shoot me an email. Thanks, guys.